We have now succeeded in getting to chapter 2, where we will be covering in detail matrix algebra methods, or what we call linear algebra systems. I'm assuming you've had linear algebra already, so the first section, which I'm calling 2.0, should be somewhat review. But we're going to cover that to make sure that we remember all the terminology and its applicability before we try to use numerical algorithms to solve these matrix systems. So let's go ahead and take a look at some of the terminology we'll be using. We're going to be talking about linear systems using matrices and vectors. We should be familiar with echelon form and reduced echelon form and how you get there using Gaussian reduction. We're then going to discuss different forms of matrices that will come up for the rest of the course called diagonal, triangular, tridiagonal, and symmetric matrices. We will discuss key terminology such as rank and dimension, inverses, and determinants. But to start with, let's look at a simple linear business model from which we want to look at constraints that are linear and solutions that optimize some business activity. So with that, let's introduce a linear system that describes some electronics business model. So in this very simplistic case, we have a company that has 3 products, X, Y, and Z. Each of these products requires the use of resistors, capacitors, transistors, and batteries. Simple, yes, but it'll make the point. The purchasing department has gotten some deals where they can get unit prices optimized for each of these 4 components under certain constraints. So let's take a look at these constraints. And of course, the purchasing department and marketing departments will throw in some of their constraints of their own. First of all, our finance group has said you can't make a shipping lot that costs more than $1,000. We're going to push it and say that the shipping lots will be exactly $1,000, which probably isn't the best way to go, but we'll do that just to make the problem a little bit easier. We have been told by the purchasing department that if for every 3 resistors that are purchased, they bundle in a capacitor, they get these superior purchasing prices that you see on the table. And the marketing department has concluded that for every shipping lot, if half of the units are product X, they will optimize their sales. So that is going to be the business constraints that we're going to work under. So the main question that we're trying to ask is, how many of each product should we put in a shipping lot of X, Y, and Z? These linear constraints that we have created can be written up in terms of linear equations. So if we go back to our budget limit, our finance department is saying we can't go over $1,000 per shipping lot. So we're going to try to hit it exactly on 1,000. So we need to know how many of each component times their unit cost when added up will produce that $1,000 cost. We also have a simple equation that the purchasing department gave us, that the resistors need to be 3 times the capacitors. And we have from our sales that the product X should be half of the total, which you can see here. And we have the design constraints that say that when you look at the table in rows, that the number of resistors you're going to need is going to be 10 times X plus 15 times Y plus 25 times Z. And similarly for the other components that we have to buy. So we have now created 7 equations and 7 unknowns. And we could write it down in this very standard form of writing linear equations. We're going to modify those a bit and try to put all the variables on the left-hand side and only constants on the right. That will end up causing our last 6 equations to have a set of variables equal to 0. We'll see that in just a minute. But note that if you're trying to solve that by hand using high school algebra, you're going to have a bit of a problem. Even doing this using standard linear algebra techniques would take a bit of work. And these are the steps that you would go through. You would first align all the variables in columns. You can see here that we have put variables on the left and constants on the right. And that has required some use of negative signs in order to make that work. Our next step will be to separate the constants into a matrix and the variables, or 7 variables, into a column vector and put the result in a standard matrix vector form. So if we move to that matrix notation, there is our matrix that we're using, which really cleans up those coefficients a lot. We have a column vector that consists of the variables that we're trying to solve for, and we have also a column vector on the right-hand side, which is our constant. Now you can check to make sure this works using the standard matrix vector multiplication, and you'll see that that reproduces the equations that we had on the previous slide. So how do I solve this? Well, if I were in a linear algebra class, I'd have more than one way to go. I could take this system, which I'm now really turning into a AX equals B form, and I could invert the matrix A and multiply it by both sides of my AX equals B at the bottom and get my solution that way. Or I could put it in augmented form and do Gaussian row reduction and get my variable X solved in that way. Either way would be just fine. If we want to create the solution, I'll just sort of give it to you in advance, even though I won't take you through all of the gory detail. I could put this thing into MATLAB, which would be cheating in this course, and if you do that, you're going to get no points whatsoever. But if I did, I could get MATLAB to calculate what X is directly. And we will show you that right at the end of the course, or at least the end of this section. But in this course, we are going to do the operations ourselves. We're going to learn how to program the computer to solve what MATLAB could do quite easily for you. But it'll also show you where the weaknesses are and where we need to be careful. Now, if you want to check your work, that's okay. You can cheat a little bit. And if you use this equation at the bottom after you write your algorithms, it's a good way to find out if you made a mistake or not. That single line performs the solution to the equation AX equals B. That's how powerful MATLAB is. You can solve these things quickly, but not here. Only use that for checking your work, not for actually coding up anything. But when you do it, either your way, by hand, by coding it, or using MATLAB's approach, you ought to get a single number. And I've put it as a row vector in that form. You can check it if you'd like, and that would be the solution for this particular problem. Now, what is unsettling about that solution? If you look at that hard, you've got an impossible situation. I've got fractional components of things that can't be put in fractions. And something about that just looks kind of funny. And so there's going to be a de-optimal approach in trying to solve things that really ought to be done using linear programming methods that we're not going to cover in this class. So don't take this problem too seriously because it really isn't producing anything meaningful. I'm just using it to explain the basic terminology and the tools of what will end up being more meaningful problems that we'll solve throughout the course. So that takes us to the end of section 2.0a. Next time we are going to keep exploring other terminology that we will be using frequently throughout the course, and we'll save that for the next time.